Okay, so this whole chapter is going to be on exponents and logarithms, and exponential functions and their graphs, logarithmic functions and their graphs. And today we're going to talk about exponential functions. So if we have y equals b to the x power, where x is my function, or is my exponent, we have an exponential function. So a couple things that had to be true. My base has to be greater than 0, because if you were going to graph something like b equals y to the 0, or sorry, y equals 0 to the whatever. Oh, there we go. Y equals 0 to some power. Well, 0 to any of the power just gives you back 0 over and over again. Okay, so b has to be greater than 0. That also rules out our negative numbers. B also can't equal 1 for pretty much the same reason. If you had 1 to some power, well, 1 to the first, 1 to the second, etc. is just 1. So that's pretty boring. Okay, but x, our exponent, could be any real number. So that's where our domain down here comes from. Our domain is from negative infinity to positive infinity. It's all real numbers because x could be any real number. So this graph does go left and right forever. You guys might remember these like your exponential growth functions. It looks something, that's not a great drawing, but you get the idea. They kind of went like this, and then eventually they shot up very quickly. You might remember them last year from Algebra 2 honors. Our range, though, these graphs do have horizontal asymptotes. So we'll get a horizontal asymptote. It'll get closer and closer to, and by default, if there's no multiplier and no shift, it's at 0, y equals 0. So you can see that down here in our notes, y equals 0. So our range goes from 0 to positive infinity, and our y-intercept is at 1. Because if we were to plug in 0 for x, anything to the 0 power is 1. So always get that nice 1 for a y-intercept. Okay, if b, that base, happens to be some value greater than 1, it's increasing. So for instance, if I had 3 halves, it's not great parentheses, 3 halves to the x power, this is still a value greater than 1, so this is still increasing. It would be exponential growth. But if my b value is between 0 and 1, so let's say we had the reciprocal there, 2/3 x, this model's exponential decay. So rather than going up, this graph actually gets closer and closer to the asymptote as you go to the right. It shoots up on the left. Something like that. Well, I don't know what's happening there. So let's do our first example, which is towards the bottom here. Okay, so our first example, we're going to graph y equals 2 to the x power. So I've got some points to plug in here. Let's start with the easy one, the even or positive numbers. So 2 to the second power, so we're plugging in for x there, is 4. So the point 2, 4 is on my graph. When I plug in 1, 2 to the first power is 2. So the point 1, 2 is on my graph. When I plug in 0, anything to the 0 power is 1. That gives me my y-intercept, which we talked about earlier. 2 to the negative first, if you remember with exponents, to make this negative exponent positive, you change its place in the fraction and make it positive. So we get 1 over 2 to the first power, or 1/2. So at negative 1, I'm at 1/2, somewhere in there. And if I plug in negative 2, we're going to do similarly 1 over 2 to the positive second power, or 1/4. So at negative 2, I'm at 1/4. And if I kept going that way, I'd get 1/8, 1/16, 1/32, and we start getting smaller and smaller and smaller, but we never actually get to 0. So this is why these graphs have a, oops, wow, that got really squiggly. That's why these guys have a horizontal asymptote. We'll just bear with it at 0. And by the way, there would be a nice point if we had plugged in 3, 3, 8 would be on that graph. Okay, so there's what my graph would look roughly like. Okay, our second example, down towards the bottom here, if I have 2 to the negative x, we can think of this as 2 to the negative first to the x power. Because a power raised to a power, you'd multiply them, and that's equivalent to negative 1x. And the reason we would do that is because 2 to the negative first is 1/2 to the x power. Okay. So now I don't have to worry about a negative exponent. You might remember, though, if you thought back to functions in this form, a times b to the x minus h plus k. We did these a little bit last year. When x is negative, like your multiplier is negative inside of here, this actually, rather than reflecting over the x-axis, it's going to reflect our graph over the y. So if you imagine the function above, if we reflected this over the y-axis, it's going to come this way, and that's roughly what our graph is going to look like here. Also, for what we talked about earlier, because b is between 0 and 1, it's 1/2, this is exponential decay. So let's put some points in here. We're going to use 1/2 to the x. So 1/2 to the second power is 1/4. So at 2, I'm at 1/4. When I plug in 1/2 to the first power is just 1/2. So we're up at 1/2. When I plug in 0, again, anything to the 0 power is 1. So we get that default y-intercept of 0, 1 again. When I plug in negative 1, okay, properties of exponents allow us to distribute to the top and bottom. So I get 1 to the negative first, 2 to the negative first, and to make them both positive, they both change place in the fraction. And we end up getting positive 2. And similarly here, 1/2 to the negative second gives me 1 to the negative second over 2 to the negative second. Doesn't want to write some of the time here, sorry. Which gives me 2 squared over 1 squared, or 4. It's a lot of calculations there. You can also kind of follow the pattern here, right? It's getting twice as big every time I move 1 x unit to the left, or it's getting half as big, or my y values are cut in half every time I move 1 x unit to the right. So similarly, this 8 point would be up here if we continued our pattern. And so my graph comes down roughly something like that. This pen's not very good at drawing accurately. Nice smooth curve in there. And there's our exponential decay graph. Okay. Next, we're going to take a look at what some of those things do. I kind of preluded this a second ago with the y equals a times b to the, holy cow, I don't know what I just did. Y equals a times b to the x minus h plus k. Yeah, there it goes again. Plus k. All right. So let's check this out. If we graph some of these, let's pull up our graph. Okay, so we're going to do 4 to the x. Boom, there's my graph. I'm actually going to add in, you can do this through the menu, or not. What just happened? Yeah, give me my axes back. Menu, view, grid, aligned grid. So you get that nice grid in there. That'll make it easier to see. I'm going to hit tab. Let's graph our next one. And see if you have a guess as to what's going to happen when I do this plus 2. Does that shift my graph up 2? Does it shift it right 2? Does it shift it left 2? What does that plus 2 do up in my exponent? And I'll give you a hint. This is where like h would be. So take your guess. Let's shake it out. And boom. If you follow your nice y-intercept 0, 1, and end up moving left 2. Okay, so let's say we take that function, 4 to the x minus 2, or x plus 2, and we subtract 3. Okay, so minus 3, not in the exponent. What do you think that's going to do to our graph? And it's going to shift down. So we went left 2 to get to the red graph, and down 1, 2, 3 to get to the black one down here. So just kind of reiterating some of that function form. We did some of those transformations. What about if a is negative? Well, if I make a negative in front, let's see. What if I put in negative 4 to the x plus 2 minus 3. There it is. Shifts our graph, reflects over the x-axis, makes it go upside down. So very similar to the a values we saw beginning of the year as well. All right. Next thing we're going to talk about is e, the number e. You learned this last year. E is irrational, much like pi. As a decimal, it goes on forever and never repeats. And its approximate value, like pi is like 3.14. We generally go out one more decimal place for e. It's about 2.718. Okay, so we've got a few extra decimal values here, and that goes along with the table we're going to fill in. So y equals e to the x, we call it the natural exponential function. In fact, anytime you see e, usually the word natural follows pretty closely behind. Natural log, which we'll learn later is log with base e, etc. Okay, so they've given me a little function here. 1 plus 1 over x, and it's asking me to evaluate this. Okay, so I'm going to start 1 plus, control divide, 1 over, I'm going to start by plugging in 1 for x, so 1 in the bottom, and then 1 for my exponent. So 1 over x to the x. So if I plug in 1, we end up getting 2. So we can fill that in that table. Eventually, there we go, we get 2. Okay, pull my calculator back up. What did I do? Get back here. All right, we're going to change this out. Instead of 1, we're going to plug in 10. We plug in 10. Holy cow, that's an ugly fraction. So control enter to force the decimal. We get about 2.59. I'm just going to continue the table without stopping to write it in here to save a little bit of time. So here's 100. Whoa. Control enter. Thank you, decimal. About 2.7. I'm also going to move this. If it'll let me. Let's move this here a little bit better. Okay, so we're just going to kind of keep increasing these values. And in fact, I'm going to skip ahead a little bit. And you might notice we're starting to get very close. 2.71815, 2.71828. So we're getting pretty close to this value. In fact, if I add a few more zeros to each of these, there it is. We're getting pretty darn close. 2.71828, etc. So this is our first introduction to what's called a limit. So this is some calculus right here. So this limit says the limit of this function as x goes to infinity, as we plug in infinitely large values for x into this function, we get infinitely close to and equal to exactly e. This is actually one of the ways that e is defined. So the limit of 1 plus 1 over x to the x as x gets infinitely large gives me exactly e. Okay, so that's what limits are. We usually talk about things like at infinity, what happens when we get infinitely large numbers or small numbers. So you'll see that a lot next year in calc. Okay, next we're going to go to some of our interest formulas. You guys might remember some of these. Simple interest, P plus PRT. That's your principal times rate times time plus the original principal. The way simple interest works, if I put in $1,000, so let's say I put in $1,000, and I'm going to get 10%. Okay. After the first year, I'd have $1,100 in that account. I'd have an additional 10%, which would be $100. And every year after that, I get the 10% of my original investment. So I'd continue to get an extra $100 every year. Okay. We'll just go to $1,300. And simple interest isn't bad. 10% would be an awesome rate to get. But compound interest is better. The way compound interest works, if I start off with that same $1,000, but I get 10%, after the first year, we'd have the same amount in our accounts. I'd have $1,100. However, in the next year, with compound interest, I get to make interest off of every new amount. So now I have $1,100, and I'm going to get 10% of the $1,100, not just the initial investment. So rather than $100, I get $110 the next year. And so now I have more money. The following year, I get 10% of this, which would be an additional $121. So $21, so I'd have $1,331. Now I have $31 more. And the longer these investments continue, you can tell we're definitely going to have more money in that compound interest account. Okay, so these two formulas use a lot of the same variables, so they're defined below. A is the amount in our account after t years. P is the principal or initial investment. R is the interest rate as a decimal, and that's important. So for instance, 6% would be 0.06. Not 0.6, that'd be 60%. And not 6, that'd be 600%. So be very careful, make sure it says a decimal. N is the number of times compounded yearly. That only obviously applies to compound interest. And T is our time in years. Okay, so we've got an example below here. It wants us to calculate some of these things. So an investment of $5,000 is made to an account that pays 6% annual interest for 10 years. Find the amount in the account if the interest is compounded. So it just told me we're using compound interest. So that formula again is A equals P times 1 plus R over N to the N times T power. Okay, so if it's, let's define some of these things. 5,000 is my principal. 10 years is T, my T value, or time in years. 6%, 0.06 is my interest rate. And if this is compounded annually, that is 1 times per year. Okay, so if I was plugging in here, I'd get A equals my principal, 5,000, times 1 plus our interest rate, 0.06, over N, which is 1 times annually, to the N times T power, 1 times 10 power. So let's look at that would look like in my calculator. So that's 5,000 times 1 plus the fraction 0.06 over 1. Make sure I'm up in an exponent here, 1 times 10 power. So that's the amount I would have in my account for my annual, if this was compounded once annually. Okay, for the second example, this thing's going to be compounded quarterly. So the only thing that's going to change here is that N is now 4 times a year. Okay, so let's take a look over here. What that would look like. If I go up twice to reselect this and hit Enter, I can bring it down, and we can change N to 4. Okay, so if it's 4 times a year, I make a little bit more money. In fact, more than $100 more. So that's pretty awesome. If it's monthly, my N value would be 12 times a year. If I change my N value to 12, we get $9,096, so even more money. Almost $27 more than if it was just quarterly. And if it was daily, well, that would be 365. Whoa, somehow I lost my exponent. 365 times 10. And let's get rid of this mess. Okay, so we have to put 365 down here. Oh no, there we go. Escape is my friend, or undo. If you ever need to undo, you can do Control Z or Control Escape, undo. Alright, there we go. So at 365 I make even more money. So then the question becomes, what would happen if I compounded this thing an infinite number of times? That sounds like a calculus idea. So what happens when n goes to infinity? And there's a little proof here. I'm going to skip it, but basically we can get into this inner part here, which basically ends up being the definition of E, and eventually we get this formula. So if I go to infinity, A equals P times our natural number E to the R times T power. And this is called continuously compounded interest. If it was compounded an infinite number of times or constantly being compounded. So the last example just says basically to use this formula to see how much money we'd have with continuous compound interest. So I take my principal, $5,000, times E, and there is an E button down here on your calculator to the left of 1. And my exponents to our rate, which is 0.06, times time. So times are 10 years. And if we compare it with the 365 times a year, it is more. Not a whole lot more. We're talking about like 45 cents over the years after 10 years. So it's not a ton more, but it is more. And so continuously compounded interest always yields you the most. If you want to read through that proof, this is basically where the formula comes from. So there you go.